Hi everybody, this is our lecture on section 2.3, and this is volumes using cylindrical shells. So in section 6.2 we calculated volumes, or 2.2, we calculated volumes using perpendicular slices. Okay, this is a different method which can be used to calculate some of the same volumes and some volumes that you can't calculate or not easily calculate with perpendicular slices. So consider a region as shown. And got a function on the top, fx on the top, and g of x on the bottom. And you've got this region here. And I want to revolve this region around a vertical axis. And calculate the volume of the resulting solid. So the picture that we have is as follows. So here's that region. And now we're going to pick a vertical axis. So the vertical axis is like this, and that's x equal to v, we'll say. And then what you get is a solid, look at that, it's like a nice mustache shape, consisting of two copies of, that's made by revolving this region about that axis. So right, so something looking like that. All right, now if we were to revolve this thing around a horizontal axis, then slicing perpendicular slices works just fine. But here in this instance, it just doesn't. Okay, so I mean, it might work. Perpendicular slicing could be used to calculate the volume of this region of the solid, the volume of the solid obtained by revolving around a horizontal axis. This new situation requires a new strategy. Okay, doesn't have to, but in general it does. So there are plenty of examples of where such a solid could be calculated both using slices and using shells. But anyway, and I'll give you some examples like that just so we can calculate the same thing in two different ways. But first, let's describe the method. Okay, so subdivide. Oh, so this region here is from x equals a to x equals b. Okay, so here's the x-axis, and the region is from x equals a to x equals b. So subdivide the interval a less than or equal to x less than or equal to b into subintervals of width delta x equal to b minus a over n. Okay, and at each xi, and say that n is large. Okay, so think of n as I mean, of course, you're going to let n go to infinity, so we're going to think of n as a large number. Okay, we're not going to, the idea doesn't really sort of come through when n is a small number. I mean, of course, we're going to let n go to infinity in the end, so, I mean, n is just something big. So at xi, okay, define a cylindrical shell as shown. So here is that solid, or that region, and we're going from x equals a to x equals b, and we've subdivided into subintervals. Alright, so this is down here, x1, x2, and then we'll just say this is xi right here. xi, so on and so forth. Okay, so now, and here's that vertical axis right here. Now that vertical axis could be over here. Could be over there. Okay, but we'll take it over here first, and I'll show you what's the difference if you put it over there. It's not much different, but anyway, you know, it can be done differently. So at xi, consider this length right here. Well, what's this length? It's fxi minus gxi. I lost my g. That blue length is fxi minus gxi. So this is xi. Actually, let me get rid of these. Just doesn't do the picture to right. This is xi, and this is xi plus 1. Okay, let's zoom in. Okay, so consider this length right here. What is this length? It's f minus g. Oh. And now extend that length, the width of delta x. Alright, so this width right here is delta x. And now rotate that rectangle around this vertical axis. Right about there. Okay, so we've got this rectangle revolved around, on the other side, revolving around the x-axis. So the shape that you get is this cylindrical shell, you know? Right, so we've got this shell shape here. And the thickness of that shell along the top, along the top is delta x, right? So we estimate the solid by calculating the volumes of these cylindrical shells, adding them up, and then letting n go to infinity. Okay? What is the volume of this cylindrical shell? Okay, well, the volume of a cylinder, so probably want to think of these things as sort of broad and short cylinders rather than tall and thin cylinders. So more like a tuna can rather than a soup can. So what is the area of a circular cylinder? Or, sorry, the volume of a circular cylinder. All right, so here's your circular cylinder, and you've got a radius like that. And you've got a height like this. All right, so the volume of the cylinder is equal to, it's pi r squared times h. Pi r squared times h. So now if you've got a shell, well, it's a large cylinder minus a smaller cylinder. All right. So you've got a radius, so kind of like an air filter. Well, I guess those types of air filters are maybe a little before your time, but an air filter on those old cars from the 70s and 80s, those ring-shaped ones. So you've got a smaller radius, and then you've got the larger radius. So the volume is the volume of the larger cylinder minus the volume of the smaller cylinder. So the volume is equal to pi r squared h minus pi little r squared h. Right, they're the same height. So it's pi h big R squared minus little r squared. So that's pi h big R plus little r big R minus little r. Okay? So that's the volume of that cylindrical shell. So let's apply this to the situation up here. Okay, so the blue cylindrical shell actually, let me arrange the notes a little better here. Oops. Alright, the blue, cylindrical shell has height, well, the distance from here to here. It's f minus g, right? Has height equal to f x I minus g x I. Large radius, well, it's the distance from here, from xi plus 1 to the vertical axis. So that's xi plus 1 minus v. If the v is over here, then it's v minus xi. But we'll talk about that later. Just assume that the vertical axis is to the left from now. The big radius is x I plus 1 minus v. And the little radius is the distance from here to the axis. Right? It's this distance here. That's the little radius. And the big radius is right here. Not much different, right? Not much different because these cylindrical shells should be very, very thin because we're letting n go to infinity. The thickness of those cylindrical shells is delta x, which is b minus a over n. So little radius is xi minus v. Actually, let me leave that in there. So color purple. So this is the little radius right here. And I can erase that. This is the big radius right here. And the difference between the little radius and the big radius, of course, is just delta x. All right, so down here, so now the volume of the shell is equal to, well, this formula right here, pi h capital R plus little r, capital R minus little r. Right, so this is equal to pi, and then the h was fxi minus gxi. Right, the height and the difference between the functions. Big R plus little r is equal to 1 second. Big R plus little r. Yeah, big R plus little r. Well, let me think. What's the right way to say this? Let's just write it as big R plus little r for the moment. And then big R minus little r is just xi plus 1 minus xi, right, which is delta x. The difference between the xi's is delta x. I guess I didn't say what xi was, but xi is the usual thing. Xi is equal to a plus I delta x. So x1, x2, x3, x4, they all differ by delta x. So that's exactly what we've got here. So this is equal to pi times fxi minus gxi. And now, when for delta x really small, right, which is what it's supposed to be, little r, or big R plus little r is approximately equal to big R. Right? The radii are, is approximately equal to 2r, or 2 little r will do. It's approximately 2 times the little radius, because there's supposed to be very little difference, right? And we're going to let delta x go to 0, because we're letting n go to infinity. So the difference between little r and big R is not that much, right? So this is approximately equal to 2r. And then this is delta x. Right, so this is equal to pi times fxi minus gxi. Let's put 2 pi. 2 pi fxi gxi x minus v. xi minus v delta x. So there it is. That's the approximate volume of the cylindrical shell. Of the cylindrical shell. All right, especially with the approximation getting better as n goes to infinity. As n gets larger. Okay, so now the sum, all right, so that's one shell. That's that blue shell we have shown here. And that's the approximate volume of that shell in terms of F, G, and X. So now the volume of all the shells together is the sum I equals 1 to n 2 pi fxi minus gxi xi minus v delta x. So this approximates the volume of the solid, and the approximation gets better as n gets larger. Right, so same idea from before. So therefore, the volume of the solid obtained by revolving that region around the vertical axis is the limit as n goes to infinity, the sum I equals 1 to n 2 pi fxi minus gxi xi minus v delta x, which by definition is what? So we've got a function with respect to xi. So we have a function with respect to xi multiplied by delta x. And we're summing that up over xi and then letting n go to infinity. So by definition, what is that? Right? A function of xi, so this is some function, hxi times delta x. hxi times delta x, summing up the xi's and letting n go to infinity. It's the integral of h from a to b, as before. So you see that? We've used the integral in several different ways. I mean, we have the classic area calculation. We've got this area calculation between two curves with volumes by slicing, and now volumes by shells. So it's interpreting the integral in different ways, all coming from the definition, right? The definition is that the limit as n goes to infinity, sum I equals 1 to n, and some function hxi delta x. That's by definition the integral from a to b of hx dx. So here the function h is this thing right there. Okay? So that's what we got, which by definition is equal to the integral from a to b of this function. 2 pi fx minus gx x minus v dx. So that's the Shell's formula. So there's different situations in which, I was talking about, and that's when the axis is to the left of that region that you're rotating. So the axis of rotation is to the left of the region. It could be that the axis of rotation is to the right, in which the only difference is as follows. So let me summarize. So let me get that picture. So we've got this region here. So for similar calculations, or volumes by shells. Alright, so the first one is you have your region, F above and G below. Shouldn't have erased that one. And x equal to v is here. And then you're going to rotate this guy like that. Okay, you're going to round that x equal to v. So this, the volume, is the integral from a to b. It's the one we just did, this one right here. 2 pi height. So the height of the cylindrical shells is f minus g. Right? Top minus bottom. X minus v, that's kind of the radius of the shells going around the vertical axis. Dx. It could be that the axis is to the right, in which case all it is it's v minus x rather than x minus v. So that's situation 1. Situation 2. So x equal to v is over here. And we're rotating that way. So here the volume is the area from the integral from a to b. Height of the shells, or 2 pi times the height. Now v minus x, because the radius of the shells going around here is right minus left. So v minus x rather than x minus v. And that's the only difference there. So that's the height of the shells right there. That's the radius of the shell. Height of the shell, radius of the shell. And both as positive numbers, right? Because the v is bigger than the x, in this case, you have to do v minus x to get the positive number. Because x is bigger than v, in this case, you got to do x minus v. Right? No big mystery there. And then you can also do these things around horizontal axes if you've got this kind of thing. So here is x equals f of y, x equals g of y. Let me see. Let me make that bigger. So this is x equals f of y, x equals g of y. So here we've got right minus left. And then if we've got a vertical line, y equals v, or horizontal line, y equals h, and we're going to rotate around this guy, then the volume of the resulting solid is the integral from a to b. All right, where a and b are these numbers here, a, b, integral from a to b. The height of the shell, so here the shell's height is right there. Do it in red. So here's y, and here's the height of the shell right there. Come on. Height of the shell right there. Right, so the height is fy, 2 pi fy minus gy, and then the radius of the shell is y minus h. Larger value minus smaller value, dy. Alright, and then situation 4, you got the same picture, but the horizontal axis is above that solid, that region. And we're rotating around that. So same formula, just instead of y minus h, it's h minus y. Okay, so 4 very similar situations. All right. So h minus y. Let's do an example. All right. One moment, I'll be right back. Okay. So here's the example. So let's take the region between the parabola y equals x squared and the line y equals x. Okay, that region there. And let's rotate this guy around the vertical line, let's say x equals 2. All right, so this is 0. This point right here is 1. And then over here is the line x equals 2. So we're going to rotate this guy around that axis. And then we're going to get the solid looking like, like that. And we're going to calculate the volume of that guy. All right. So we've got some kind of volcano looking shape there. Okay, so revolve the region and calculate volume using shells and, again, using perpendicular slices. Okay, so we're going to calculate it in 2 ways and see that we get the same answer. All right, let me copy the picture. Okay, so first with shells, okay, pick an x value in your range from 0 to 1 and draw like a line there. That represents the height of the shell and, the distance, so that's x, and the distance from here to here is the radius of the shell. Right, so this distance is 2 minus x, and the height is top minus bottom, x minus x squared. Right, and this is 2 minus x, right? Because the 2 is bigger than x, so you got to do 2 minus x rather than x minus 2. And the height of this guy here is top minus bottom, x minus x squared. All right, so the volume is equal to the integral from 0 to 1, 2 pi, right, top minus bottom, and then 2 minus x. All right, so we can calculate that. So 2 pi integral from 0 to 1, and I guess we're going to have to multiply this guy out. So we've got 2x minus 2x squared minus x squared plus x to the third. Is that right? So 2x minus 2x squared minus x squared minus x to the third. So that's 3x squared. So we've got 2 pi, and the antiderivative is x squared minus x to the third plus 1/4 x to the fourth from 0 to 1. So at 1, you just get a quarter, right? So you just get pi over 2. And at 0, you get 0. Alright, so the volume of that solid is pi over 2. Now let's do slices. So for perpendicular slices, alright, we must look at this. So that's one for, this is the x-axis. That's the y-axis, but we need to look at it in terms of y rather than in terms of x. Because the axis that we're lining the solid up along is this here. This is 0 and this is 1. Right? This is the axis along which we line up the solid. Okay, so what are these functions? So this is x is equal to y, and this is x equal to square root y on the bottom there. X equal to y, or not on the bottom, but on the bottom, on the inside, I guess. Okay, so now at y, at a value of y, what is the perpendicular slice? The perpendicular slice is right here. Right, it's the, again, that washer shape. Right? So the outer radius, the large radius of that perpendicular slice is the distance from x equals 2 to x equals y. Right? So the larger radius is 2 minus y, the distance from x equals 2 to x equals y. The little radius is the distance from x equals 2 to x equals the square root of y. So 2 minus square root of y. So the area of the slice at y is what? It's pi times big R squared minus pi times little r squared, which is equal to pi times 2 minus y minus pi times 2 minus root y squared. So the volume is the integral from 0 to 1 a of y dy, right? The perpendicular slicing formula. It's just the integral from 0 to 1, the area of the slice. Right? And the area of the slice is this washer shape. Right? So it's pi times the larger disk minus the area of the smaller disk. So this is the integral from 0 to 1. And I'm going to put the pi out front. Pi times the integral from 0 to 1, 2 minus y squared, minus 2 minus root y squared dy. So I've got to multiply this thing out, integral from 0 to 1. So this is y squared minus 2y plus, or no, minus 4y plus 4 minus y minus 4 root y plus 4. So it's pi times the integral from 0 to 1. So y squared minus 5y plus 4 minus 4 plus 4 root y dy. So that is the integral, well, the antiderivative of that is 1/3 y to the third minus 5 halves y squared. Y to the square root y is y to the 1/2. So it's 4 times 2/3. So it's 8/3 y to the 3/2, calculated from 0 to 1. So it's pi times 1/3 minus 5/2 plus 8/3. So what we get is pi times 9/3 doubt that's going to come out to be the same. Did I make a mistake in one or the other? So plus x to the third minus 2x squared minus x squared is minus 3x squared plus 2x. So I have x squared, x to the third, plus 1/4, x to the fourth, from 0 to 1. So that just gives you a quarter. So 2 times a quarter is a half. This one is, oh, not 9/3, 1/3. 1/3 plus, yeah, so 1/3 plus 8/3 is 9/3, so that's 3. Oh no, 3 minus 5/2 is a half, right? Yeah, so pi over 2. So, same answer as before, as it should be. Right, as it should be. So it's not that every such solid, so as I was saying before, it's not that every such solid can be calculated both ways. This example you could do it both ways. Sometimes you actually need shells as opposed to slicing. So here's an example. Well, not that you need it, but it's much easier to do with shells. So here's an example that slices that can't easily use slicing. So we're just going to take the function. So this is y equals 2x minus x squared. So this is 0, this is 2, and I'm just going to rotate it around the x-axis, or y-axis. So x equals 0 is the y-axis. Right, so if you were going to use slices, well, the washer shape is this. But you can't really solve for x in terms of y. Right? You can't solve for x in terms of y. So perpendicular, I mean, you can, but it's tedious. There's a lot of tedium involved. So you can't really, since it is not easy to solve for x in terms of y, perpendicular slicing is difficult to use. Right, but shells works out very nicely. Okay, here's the height of a shell right there. Right, and it's just 2x minus x squared. And then the radius of the shell, so the height is 2x minus x squared, and then the radius of the shell is just x. Right, so that's the distance from the x to the vertical axis. This time it's x minus 0. Right, but when it was over here, like if it was like, you know, a 3 over here, it would be 3 minus x rather than x minus 3. To make sure it stays as a positive quantity. So anyway, the volume here is the integral from 0 to 2. Okay, 2 pi times the height, which is that. Right, we don't have a bottom curve. The bottom curve is just the x-axis, which is y equal to 0. So you have y equals 2x minus x squared minus y equal to 0. So it's just that function. Times the radius, which is just x dx. So let's integral from 0 to 2. I'll put the 2 pi out front. 2x squared minus x to the third. So 2 pi antiderivative is 2/3 x to the third minus 1/4 x to the fourth, calculated from 0 to 2. So at 2, you get 8 times 2 is 16/3 minus 16/4. So bring the 16 out front. 32 pi. 1/3 minus 1/4 is 1/12. And which is equal to, we can divide by 4 on both of them. 8 pi over 3. Okay? So that's a nice example that really needs shells rather than slices. Although sometimes a lot of regions can be done with both. And, you know, on an exam type situation, when I ask you to calculate a volume, you can do it either way. If, you know, whichever way applies that you like best. Okay? There's a funny story that goes along. Well, I'm not going to say. Tell stories. Okay. All right. That's the end of the lecture for this section.